Okay, so I wanted to make this video to go over a interesting relativity question, uh, mostly just because I want to get practice teaching how to do questions. Because in my once I get into my graduate studies, I'm hoping to be a TA for some professors at some point. So I figured, at the very least, this video gives me a chance to just practice talking through questions aloud, and if anyone happens to find it helpful, even better. So this question on relativity, specifically Lorentz transformations. So I'm just going to read over the question quickly and we'll get into it. So in an inertial reference frame S, a red light flashes at location x1, which is equal to positive 3 meters, and time t1, which is equal to 1 nanosecond. And a blue light flashes at x2, which is equal to positive 5 meters, and t2, which is equal to 9 nanoseconds. Reference frame S prime moves in the positive x direction with speed v relative to s, and t is equal to t prime, which is equal to 0, the origins of the two frames coincide. So at time t0 and t prime 0, which are the same, frames coincide. Both flashes are observed to occur at the same location in S prime. So the first part of the question, part A, what is the relative speed between S and S prime? Or basically, how fast is S prime moving relative to S? So it's always good to make a sketch with questions like this. So here we have frame S. This is the X direction. Or sorry, whoops, got this backwards. We have our Y and X. And then we'll have another one, which is going to be S prime. And so here, coordinates will be X prime and Y prime. And this frame of reference is moving with some velocity v relative to S prime, or to S. And this is S prime. And two events that take place, and we have information about their whereabouts and time in frame S. I'm just drawing them in S prime, but these events are happening and can be observed from either frame. So we have event 1, which is a red light, so R for red, and it happens at x1, t1 in frame S, and happens in x1 prime and t1 prime in frame S prime. Then we have another event that happens. It's a blue light. So in frame S, it happens at location x2 and time t2, and in S prime, it happens in location x2 prime and t2 prime. So we have two events happening. We know where they happen at what times in frame S, and we want to, well, I mean, there's a few steps to this question. First is just to figure out how fast frame S prime is moving, but then the rest of the question deals with finding out information about where and when these events occur in S prime. So, to start off, we are going to, looking at our equations here, I have a few different Lorentz transformations up here. So we're going to be using this equation for the first part of the question. So the change in x prime is going to be equal to lambda, or the Lorentz coefficient. So, or Lorentz factor, I guess some people call it too. So the Lorentz factor times delta x minus v times delta t. So our change in x location between the two events in S prime is equal to lambda times the change in the location of the two events in S minus v times the change in time between the two events in S. So we'll go ahead and write out the equation here. So delta x prime is equal to lambda times delta x minus v times delta t. Okay, so first we need to figure out our delta x and our delta t, and then we can pretty easily rearrange this question to solve for v. So if we go ahead and, I guess let's write this off to the side here. So in frame S, we know the locations of the events. So we have that x1 and x2, we have their locations. So the difference, or the delta x, is going to be equal to x2 minus x1. And this is going to be equal to 5.00 meters minus 3.00 meters, so equal 2.00 meters. Now, we also want to find, I guess I'll just put there, that is equal to delta x. So we also want to find delta t. And this is just the exact same idea. Delta t is going to be equal to t2 minus, minus t1. So this is going to be equal to 9.00 nanoseconds minus 1.00 nanoseconds equals 8.00 nanoseconds. Okay. And one more side note I'll make here before we go into it. So all this equals delta x prime. But in the question we're told that both flashes are observed to occur at the same location in S prime, meaning that the difference between the events, between location of the events in S prime is equal to 0. So delta x prime equals 0. So we'll just write this down. So delta x prime equals 0. And from there, we can say that if delta x prime equals 0, then this expression must equal 0. So if this expression equals 0, lambda cannot equal 0, just by definition. So if lambda can't equal 0, that means everything in here has to equal 0. Delta x minus v times delta t, right? So this has to equal 0 since lambda can't equal 0 for the total expression to equal 0. So then we can say that delta x minus v times delta t equals 0. And now we have a fairly simple equation to solve. All we have to do is isolate v and solve for it. So we can just put delta x is equal to v times delta t. All we did here is just moved it over, right? Add on this side, add on this side. And then we can divide by delta t to isolate v. So delta x divided by delta t equals v. And we have both these values. We figure them out right here. So from here we can just say that v is equal to our delta x, which is 2.00 meters, divided by our time. So this is 8 nanoseconds. I'm going to write it in seconds just because once we get our speed, it's going to make the rest of the questions later a lot easier if it's in terms of meters per second rather than meters per nanoseconds. So when you convert it, that just becomes 8.00 times 10 to the negative 9 seconds. That's the conversion from nanoseconds to seconds. So then this is going to equal 2.50 times 10 to the 8 meters per second, which is also equal to 0.8333c. So 0.833 the speed of light. If you're wondering how I got this value, you just divide this value by the speed of light, which is 3.00 times 10 to the 8 meters per second. So both of these we'll use later, so it's just nice to have it in meters per second as well as to have it in terms of speed of light. So this is our answer for part A. This is how fast frame S is moving relative to, this is how fast frame S prime is moving relative to frame S. So now we can move on to part B. Find the location of the two flashes in frame S prime. So we know the two flashes take place in the same location in S prime, so we only have one location to find. So we're actually going to use almost the exact same equation, but here instead of using delta x prime and delta x and delta t, we're just going to be using this, which is just x prime, x, and t. So basically, the difference between these two equations is this deals with where you have two different events happening at two different locations in time. Or sorry, not two different locations and time, but just two different locations, and usually a change in time at 2, I guess. So, sorry, I guess the best way to explain it is, in this you're dealing with two events, and there's a difference in their location and a difference in their time. Here you would be dealing with a single event. Although we're dealing with two events, but we can treat it like a single event because they both happen in the same place, and we're only looking for that one location. So it's okay that they're two different events. We can use either of them to solve this. So here, x prime will be the location of both of those events. They both happen in the same place in S prime. X is going to be equal to that event's location in S, and t is going to be equal to that event's location in S's. Sorry, not location, it's time in S. So we can use either of these two events for this formula, but we just have to make sure we stay consistent. So if we use x1 as x, we need to use t1 as t, or x2 as x and t2 as t. So we pick either one to use in the equation because ultimately when we get its location, that's going to be the location of the other because they happen in the same location in S prime. Sorry if that was a bit long-winded of an explanation. I'm still kind of getting used to this. So I'll just write down our formula here. So we have x prime is equal to lambda times lambda times x minus vt. So from here we can write out what lambda is. So lambda is just equal to this value here. So 1 over root 1 minus v squared over c squared. And if you remember earlier when I calculated this value here, I told you how I got it was I divided this, which is v, by the speed of light. And this is just this value in the terms of speed of light. So this is just equal to v over c. And here we have v squared over c squared. But when you have v squared over c squared, you can also just write that as v over c all squared. So really what we have here is v over c squared, which is just this value squared. So, and this will all be times x minus vt. So then we can rewrite it once more and just put this as 1 over root 1 minus 0.8333 squared, because like I said, v is v over c, that's this. When you square it, then you can just plug that in. And that's going to be times. Now, we can use, like I said, either event for x and t. I'm going to choose to use event 1. You can use event 2. It won't change your answer. As long as you're consistent, you just have to make sure if you use x2, you're using t2. If you use x1, you're using t1. So in our case, x1 is 3 meters. So 3.00 meters. And then minus v. So our v here is going to be this value. And it's easiest to use it in terms of meters and per seconds rather than c at this part of the equation, just because we're dealing with meters already. So we have 2.50 times 10 to the 8 meters per second, and that's going to be multiplied by the time. So since we used x1, we have to use t1. So in our case, t1 is equal to 1.009 nanoseconds, or I'm going to convert it into seconds here just because it's going to make our lives easier. So times 1.00 times 10 to the negative 9 seconds. Okay. And all of that is subtracted from 3 meters. Okay. So I'm not going to go through all the math here. You just really need to punch this into your calculator or do it step by step, but you know, it's all just basic arithmetic algebra. Just multiply, subtract, multiply by this value. But once you punch it all through, you should get, I believe, positive 4.98 meters. So this is the location where both flashes take place in S prime at positive 4.98 meters. Alright. And now we will move on to part C of the question. Alright, and lastly we'll look at part C here. So C is what is the separation time, if any, between the two flashes in frame S prime? Express your answer in nanoseconds. So we know the two events occur in the same location in S prime, but now this question wants us to find if they happen in the same time, at the same time in S prime, or if they don't, what's the separation between the times of the two events? So basically, how much time passes between the two events in S prime. So we're going to be using this equation here, delta t prime, or basically the difference in time between the two events in S prime, is going to be equal to the Lorentz factor, lambda, times delta t, which is the difference in time of the two events in frame S, minus v over c squared times delta x, which is the difference in location of the two events in frame S. Let's go ahead and write that out. Delta t prime is going to equal lambda times delta t minus v over c squared delta x. Okay, so from here we can write our value for lambda, which we already went over earlier, how I got this 0.833 in here, squared, of course. And then that's being multiplied by everything in the brackets here. So before I actually put in the given values, because we already have delta t and we already have delta x, we figured it out in part A, I just want to address this bit here, the v over c squared. So earlier we calculated v as 2.50 times 10 to the 8 meters per second. But we said we could also express it as 0.833 c, or 0.833 the speed of light. And so in this situation, it's a lot more useful to express it this way, because what we end up with is if we have delta t minus v, but we're going to express it as 0.8333 c over c squared times delta x, well, now this c can cancel out the c squared, so now we just have 0.833 over c. So the c from here and the squared cancel each other out, and it just makes for a much cleaner formula and a lot easier computations when you're punching it into your calculator. So from here we'll say this is equal to, so if you calculate this, it comes out to, let me see here, I have it written down, 1.8089 0.89, so times delta t. If we look back here, delta t was 8 nanoseconds. 8.00 nanoseconds minus, so we have 0.8333 over c, or the speed of light, which is going to be 3.00 times 10 to the 8 meters per second times 2.00 meters. That's delta x. You can convert this into meters per nanosecond, I suppose, but it's a little harder, or at least I find it harder at this point in the question to do that. So just remember that once you calculate this value here, what's in the brackets here, you should then you'll have a matter of seconds, and then you should convert it into nanoseconds. Or at least in my opinion, it's just easier to convert into nanoseconds after you compute this. But regardless, you'll end up with 1.8089 times 8.00 nanoseconds minus 5.555 nanoseconds. And then from there, it's just easy computation, and you end up with 4.42 nanoseconds for the separation between the two events. And that is the last answer. Hope that the walkthrough through the question might be helpful for somebody, and if I feel like it, I might make more of them. But mostly just doing it for my own practice for talking through questions out loud.